Good afternoon, everyone. Myself, Nivin. I'm from pantechelearning. I'm working in embedded systems. So, I'll be taking a seminar on robotics today. So, we'll start. So, good afternoon to everyone. And this we have 1 hour session. We'll be having a 1 hour session on robotics here. So this will be purely an introductory session to robotics. You won't be able to get any hands-ons here, hands-on examples here. So we'll go through robotics and like history of robotics, and then currently contemporary robotics, and then what are the specific things that you can use, specific tools and softwares that you can use in robotics, that type of things. We'll go through that. So I'll start with this definition here. So first of all, we'll see this definition of what is a robot. So robot can be like it can we can it is not just a it can have like so many different type of definitions. But in a robot, in the most in the most contemporary sense, it is we can define a robot this way. A robot is a machine, especially one programmable by a computer, capable of carrying out a complex series of actions automatically. Robot can be guided by an external control device, or the control may be embedded within. Robots may be constructed to take on human form, but most robots are machines designed to perform tasks with no regard to how they look. So this is a definition of robot that we use these days. Any type of robots that we use these days. So all the robots that are designed and manufactured these days, they all have programmability. They can be programmed, and they're flexible, and they're developed for not just for single task. You can devise them for multiple tasks, not at the same time maybe. And also, if we have an intelligent robot, the AI based robot, then it can do multiple tasks based on the situation. Whatever the situation arises, based on that it can choose a task. So the situation doesn't have to be a specific thing like a command or a specific if condition. It doesn't have to be like that. It could be like a could be like a analysis of a complex parameter, like some kind of a environmental characteristic like temperature or something. Based on that, it can deduce something. Deduce in the sense we have already trained it. Based on that training data, it can deduce that this is going to happen. So we need to it need to be careful. So like that type of predictive behavior can be can be implemented in a robot. So these are like a no like the new type of robot. So this type so this definition fits very well with the robots that we use these days. A robot machine, especially one programmable by computer. So a computer we should be able to program the robot through a computer, capable of carrying out a complex series of actions automatically. So it should be an automated system. It could be guided or automated, but even in guided case, once you give a single command, it should be able to perform a number of tasks based on that single command. Like if we go and pick something, means it should be able to, the robot should do many things. First of all, it should identify what object it needs to pick. So it identifies the object, and already it has trained that we have trained the robot to detect that object. So it will activate the camera and it will look around for the object. Once it recognizes the object, next localization. Next, the robot need to find out where the robot is where is the origin. what is the origin location of robot, and then it needs to next thing it needs to determine is the location of the object that it need to pick. So based on these two locations, then it needs to make a path and navigate to that object and then pick up the object, and you return it to the origin position. So that could be done by the robot. So by giving a single command, go pick this object, we can activate the robot and give it the command. Then the whole thing will be automated. All the finding out where the object is, and finding out its local position and the object position, navigation, all these things are now automated. So the even in guided systems, there has to be, we have to include some automation. It doesn't even have to be this type of complex autonomous robots. It could be like simple robots, manipulated robot, pick and place robots, simply fixed in one place. That type of robots can also have multiple steps in a single command. Robot can be guided by an external control device, or control may be embedded within. So the external control device, like you have seen, you have seen drones. So these are like quadcopters. So uh, these can be controlled through a remote control. So mostly these days it is used for surveillance, or cinematography, and like detecting for other type of mapping. You can use lidar sensors, 3D lidar sensors to map an area. So you can fix the sensor on a drone and you can fly the drone over the terrain. So it will map the entire terrain and it will give a 3D model, and using softwares we can create a 3D model of that area. So you don't need to so the conventional type of mapping methods are very obsolete compared to what we like today's robotic technology that is integrates all these different technologies in one into one system, like for mapping or for navigation, localization, detecting, different type of parameter analysis, all can be integrated to one single system. So we can control it like in case of a drone. Otherwise it could be fully automated, like a surveillance robot, that a futuristic drone robot that doesn't have to be controlled by anyone. It has a particular area, roaming area, and in that area it can roam around, like it's a flying drone, so it can roam around in that area, and it should be able to detect certain things. It could be used for surveillance, to see if there are any people there, or could be used for other purposes, like if you have an industrial area and for fire detection at night time or daytime, any type of small fire incidents, or smoke or any other type of mishaps can be detected using this robot, using this type of drones. Then robots may be constructed to take human form, but robot, like we have when we say robots, we first thing that comes to our mind is a humanoid robot that has that looks similar to a human being, with the head, hands, and body, and legs, and everything. But that is not very practical in most cases. Most robotic applications, a humanoid robot is not a very practical thing. Most robotic systems, it needs to be more flexible based on the task that you need to perform. So for example, if in a assembly line, we don't need to have a humanoid robot. We can just need to have manipulators. They should be able to pick things, and there should be welding robot, or picking things, so so different type of manipulators needs to be fixed to a position, and they can move around based on the programming. They can move around in the fixed position and do things based on that. So that in that case, the robot doesn't have anything like any similarity with a human being. So most of the robots are not humanoid robots. They're not constructed to take a human form, but robots are machines designed to perform tasks with no regard to how they look. So this is like a definition of a modern robot. Then in So before going into the more into robotics, we'll see just the history of robotics. Throughout this slide, we'll see the throughout these slides, we'll see history of robotics. So mechanical automata and motor-driven robots. So the mechanical automata, like robotics, actually not maybe in the sense that we use right now, but in a different way. It already existed even centuries ago. Like in ancient Greece and Egypt, they used to have water-powered ceremonies. These are like different type of water powered structures and systems. They were mostly used for entertaining, so it was for entertaining of the elite class. So water powered ceremonies. And 14th century to 19th century, Europe, clockwork driven for entertainment. So another type of entertainment, like entertainment system, like clockwork driven, like using cogs and clock spring mechanism. Different type of robots were able, people were able to develop different type of robots. These weren't actually useful in any applications. They were you cannot make a system that can like carry weight or balance itself or determine its orientation. That is not possible at that time. It is only like we can make simple things that can like a metal bird that or something like that. So it will do something like a key car that we have for toy car. You can give the key and then it will work for some time continuously. So it is purely for entertainment purpose. There is no practical sense to that. Then with the invention of with the arrival of new technologies and with the industrial era, the modern industrial era, with the industrial revolution, more new research started in that particular front of robotics. Then there was motor driven robots. So the motors were invented already in first half in 1920s and before that. So people use these type of motors to create invent a new robot. So first motor driven robot was built in 1928, almost 100 years ago. First motor driven robot was built in 1928, and then second then more modern version was built in 1961 called Unimate. So the Unimate was the first industrial robot. Then in 1967, Shaky, autonomous mobile research robot. So it was a research robot. Then 1969, Stanford arm, dexterous electric motor driven robotic arm. So this is Unimate. It was developed by George Dowell. Unimate was the first industrial robot which worked on General Motors assembly line at the Inland Fisher Gate plant in Ewing Township, New Jersey in 1961. So it was built in 1961. It was you can see the structure here. It is a single arm robot and it has a gripper at the end. It has a endpoint effector at the end, and using that endpoint, so it is mostly used for picking things. So this was an industrial first unit. It is the first industrial robot ever built. So it's called Unimate and was used in General Motors assembly line. So that the robotic research was first done for the industrialists. Like already assembly line production was already implemented, but using people. So in General Motors and that type of Ford and General Motors, that type of automobile manufacturers already started this type of assembly line production, but it was fully based on people, and then they started introducing robots to this. Then Shaky by Charles Rosen. So Shaky, the robot was the first general purpose mobile robot. So it is a general purpose mobile robot to be able to reason about its own actions. So it is general purpose. That means it is not just for a specific task. You can write a program and you can make the robot do different multiple tasks based on the program. And while other robot would have to be instructed on each individual step of the step of completing a larger task, Shaky could analyze commands and break them down to basic chunks by itself. So the other robots, in other cases, you have to what you need to do is you can only it is designed for a specific task. Like in case of Unimate, it is designed for a specific task. It can only do that task. You can just turn on the device and give controls, and you can make it work in a particular way. But in case of Shaky, it is a general purpose robot. That means it has a computer inbuilt, and you can program the robot, and you can give larger task, and robot is on its own. It is able to break down this task into smaller chunks and execute the whole larger task based on the small task. So by the look of it, you can see this is a prototype. This is a research level robot. It is not used in any industries. It's a research level robot for the future development and research. This one is a fully finished product. And another one, Stanford Arm. This is also another research level project that was created in Stanford University. So that's why it's called Stanford Arm. Stanford by Victor Scheinman, and the Stanford Arm is an industrial robot with 6 degrees of freedom, designed at Stanford University by Victor Scheinman in 1969. So it has 6 degrees of freedom, so it can move in multiple directions in 3D plane. So that's why it in 3D space. That's why it is more interesting than the Unimate. So Stanford Arm is also like Unimate. It's a manipulator. It's a fixed manipulator, but still it has multiple degrees of freedom. It has 6 degrees of freedom. So it is much more flexible than, and has much more. We can use it in much more applications than Unimate. So then robotic development today. So if you go into more robotics beyond history, what is currently happening? So I won't be able to cover all the different things happening in robotic systems. So we'll just talk about what things that are useful for you. So if we take like these days, automation is a big thing right now. Like so many, like if you take self-driving cars or self-driving vehicles, there are like so many research is going on that same thing right now. So much things are implemented. You can watch different type of videos. So if you take the example like Tesla cars, already have implemented this type of self-driving capabilities, but it is not fully standardized. Still they are developing so many things, and there is a collective of different manufacturers, different automobile manufacturers coming together to make a single standard for all autonomous cars. So we cannot discuss in detail here because that won't be useful for you. So we'll be discussing about ROS. So when it comes to automation, in robotic automation, ROS is a very important factor. Like in case of software development, how Linux would help any developer. The same way in case of robotic development, ROS can be used. So for same as in case of Linux, it is an open source system, so you can develop things on your own. You can change it the way you want, and you can contribute to the overall development of the system itself. The same as that, ROS is also same. It's an open source system, so anyone can use it and they can contribute to the ROS environment, or they can simply just use ROS for whatever, implementing different type of robotic systems. So in previous days, so ROS means robot operating system. So it's an operating system. It is not like a conventional operating system. Like when we say operating systems, we can say like Linux, Windows. So these are like operating systems, general purpose operating systems. But RO is not exactly like that. Will explain. Will discuss all that while we go into more details. So ROS is mainly used for, so in previous cases, like in the last decade, in 2000s or after that, if you want to implement a complex robot, the same thing that I've just described before, a robot that should be able to pick any object. So to pick that object, it has to go through all those steps. First, it needs to identify what object it needs to pick, then recognize then go around and see where the object is, and once it detected the object in any place, then it should be able to locate itself and the object. So there are like so many things happening here. The robot needs to have an object recognition program that should be trained with the specific object that it need to identify. So that object recognition program is running at first, and then so there is a camera that is activated. So robot should be able to take commands. So commands should be given through a mic or a mobile phone using Bluetooth or Wi-Fi, whatever way you want. Then once the command is received, the robot should run the object detection program, and then once that is done, object is detected, it should localize itself. So there should be a map, a surrounding map. In that map, it should be able to localize itself, and then it should be able to localize the object that it needs to pick. And then after that, it should be able to make a path. So create a path. So and then it should be moving to that path. So this first thing we can call it as a part of AI, or called deep learning. So we can use deep learning to detect the object, whether it is any type of object it is, whatever. If you train for that object, then you can. So that comes under deep learning, and then the whole other process can be categorized as SLAM. So SLAM means self-localization and navigation. Self-localization and navigation. Self-localization and mapping. So that means a robot should be able to localize itself in an environment, in a mapped environment, and then it should be able to create a path to a goal location, and it should avoid all the obstacles, any obstacle that is already there, or any object that comes after the path is created. So avoiding all those things, it should reach the goal location. So this whole thing can be, this is, if you wanted to implement this in before ROS, it will be very hard. You have to write all the things from scratch. You need to write every single code from you can use different type of pathfinding algorithms to write the algorithm, and then localization, you have to write some program for that, and then for DC motor manipulation, you have to write some program for that. So you need to implement everything from the lowest level. But with the ROS, it becomes more easier, because of all these things are already, so many of these things are already implemented in ROS. For example, localization can be done using ROS, and pathfinding can be done using ROS. And we can integrate camera, a 2D camera or a 3D camera with the robotic system, or you can integrate a LiDAR sensor, 2D LiDAR or 3D LiDAR sensor with the ROS system, using existing packages in ROS. So that is the advantage of using ROS. You don't need to you don't need to develop anything new on your own, like anything complex. So that will take so much time. So the ROS is used to not just by it is not just used for academic purposes or small development purposes. It is used in industrial cases, and it is mostly used in development for research and development cases. So ROS is actually, you don't need a multi-person team to create an ROS application. You can as a single person, you can create to your own ROS application easily. So then this is just a description of what is ROS. So robot operating system, ROS, is an open source robotic middleware suite. Although ROS is not an operating system but a collection of software frameworks for robot software development. It provides a services designed for a heterogeneous computer cluster, such as hardware abstraction, low-level device control, implementation of commonly used functionalities, message passing between processes and packages. So it is used in a, it is not like a conventional operating system, because it is implemented in a implemented in a cluster of heterogeneous computers. So these computers, heterogeneous computers means they are like different type of computers. So you can have a Windows system, a 86 architecture Windows system, to run one part, and then you can have a Raspberry Pi or a Jetson board or Edison board, any type of single board computer that could be based on ARM architecture. That is a totally different architecture, and it could be running Linux OS. So that the single board computer, the mini computer, single board computer is running a Linux OS with the ARM architecture, and our laptop is running Windows OS or Mac OS with the 86 architecture. So that means these are totally different environments, and we could club using ROS. We can combine these two, and these two hardwares will be able to, computers will be able to effectively communicate to execute different tasks. And you can also integrate lower level hardware like microcontrollers, small microcontroller boards, whether it is Arduino or ARM or any other PIC or any kind of microcontroller board. You can integrate a lower level microcontroller board to that same system. So all these hardwares are different type of things, and then we can have like a LiDAR sensor and 3D camera, 2D cameras, GPS, and other type of odometry sensors, and then we can have wheel odometry data. By using wheel encoders, we can get the wheel odometry data, and by combining all these things, we can have an idea of how the state of the robot. So that is a very important factor in case of robotic operating system, because it can combine all these different data and make it into a single stream of single state of robot, and it can calculate a single state of robot using all these different robot and its environment using all these different data. So the data from a 3D a stereo camera or 3D camera will be totally different from a data from a 2D LiDAR sensor. So LiDAR sensor will give a 2D map with the lines, point cloud lines, and then if you take a 3D camera, it will be giving a 3D image, a space structure of the environment. Then if you take an odometry sensor, like if wheel odometry sensors and wheel encoders, if you're getting the odometry from wheel, then wheel encoders means they're just simply tick sensors. So with each rotation they'll register one tick, so that we can count the number of the RPM of the motor. In real time we can count the RPM of the motor, and also you can count the direction in which the wheel is rotating. So it can have using that we can know how the robot is moving, in which direction it is moving, and how much speed it is moving. So all these feedback are given. So using all this data, a closed loop is created using all this data. All this data is we can get all this data from the hardware part, and then that is given to the processing units, and they'll process it, and they'll give the different type of parameters that needs to be given, like the motor speed, velocity of the motor, direction of rotation. All these things are given to the given as output. So that all these things are combined in a one single system with the multiple hardwares. So that's called a ROS, robotic operating system. And it has a different type of capabilities. It's not just for SLAM. You can implement so many different things using robotic operating system. And one good thing about robotic operating system, since it is open source, you can go online and you can study it yourself. You don't need any help, but you can also refer to different forums and for different tutorials for studying about robotic operating system, or you can read books about robotic operating system, ROS or ROS2. So ROS project was started in inception, the creation of ROS. ROS project was started in 2007 in Stanford University under the name Switchyard. Later on in 2008, the development was undertaken by a robotic research startup called Willow Garage. Then afterwards, the major development in ROS happened in Willow Garage. In 2013, the Willow Garage researchers formed an open source robotic foundation, OSRF. ROS is actively maintained by OSRF now. It's actively maintained by OSRF right now. So in case of what is ROS, hardware abstraction and low level device control. So like hardware abstraction in the sense like hardware abstraction is used for accessing hardware using a hardware components using a using higher level software layer, accessing hardware layer not directly but indirectly from a software layer. Software layer means a high level any kind of application software. So software won't be able to access the hardware directly, but there will be an abstraction layer. Hardware abstraction layer will be there. So using this abstraction layer, there will be the abstraction layer will act as a middle man between the middleware between the softwares and the hardware. So hardware abstraction and low level device control is possible, then created by California Willow Garage, so now maintained by open source robotic foundation. So ROS includes all these different things like plumbing, tools, capabilities, ecosystem. So we'll discuss all these. So then what is hardware abstraction? So hardware abstraction are a set of routines in software that provide programs with access to hardware resources through programming interfaces. The programming interface allows all devices, particular class C hardware devices, to be accessed through identical interfaces, even though C may contain different subclasses of devices that is provide a different hardware interface. So C means it is a type of class of computing devices. Like normal type of PCs and all these things comes under C type of class C. So class C hardware devices. It's a so they are identical. But they're not exactly the same. Different. So because C may contain different subclasses of devices. So the hardware abstractions are used for it's the same thing that I explained just before. It is in between the actual hardware and the software that we need to use. There will be a hardware abstraction layer. The hardware abstraction layer has a map of the all the hardware and how to control all the hardware. Everything is given. So that at the software level, you don't have to write all that. You can just give some commands, and you can give some have to follow some protocols to access these hardwares. So all that can be done through the hardware abstraction layer, hardware abstractions. Then plumbing, ROS provides a publish and subscribe messaging infrastructure. So plumbing in the sense it is for message transfer, sending and receiving message. So I've told you about in one ROS example, SLAM, simultaneous localization and mapping. In SLAM, a robot can move from one point to another point. So in that case, the robot should be able to do all these different things. It should be able to first map the entire environment, like whatever the entire area that the area. So lidar is more, so we can use an indoor robot, this in case of an indoor robot, and we can use a lidar sensor and 2D lidar sensor and map the entire area, and using that map it can navigate from one point to another point. So it's not that simple, one point to another point. There is another so many processes happening at the same time for this to work, for this happen. So the, for example, the robot should be able to initially the goal location, once we given the goal location, it will find a path in the map, in the overall map it will find a path with by avoiding all the different obstacles, all the possible collisions, avoiding all that, it will find a path, and based on the path it should move in one direction. So it robot could be in one orientation. So then the message should be, the command should be sent to the microcontroller. The microcontroller is controlling the DC motors. So the DC motors should rotate, DC motors or servo motors or whatever it is you're using. So what that motor should rotate in a particular speed in a particular direction. So that can be given as velocity commands. So these velocity commands need to be sent from whatever device that we are using for mapping. It could be, we can use a single board computer for that. So the data should be sent from this velocity vector value should be sent from the ROS, the single board computer, to the microcontroller. So this is a messaging system. So here ROS uses publish and subscribe model. So publish and subscribe model means in microcontroller will subscribe to a particular topic that so it is publish and subscribe. It has the same sense as the normal publish and subscribe that we use. Like if you take a publication like a newspaper or a weekly, whatever, if you subscribe to that on a regular basis, you will get that publication, whether it is a magazine or a newspaper, you will get it on a regular basis if we subscribe to that particular newspaper. So the newspaper is a topic, so you can subscribe to anything whatever there is, you can subscribe to that. So if you subscribe to particular, like if you subscribe to Times of India, you will get Times of India every day. So if you subscribe to Hindu, then you will get Hindu every day. So that is depends, so that the title of the publication can be set to be a topic. So same idea can be used here for in this publish and subscribe. So if the microcontroller needs to get the velocity commands, velocity values whenever it needs to move, it can subscribe to a topic. So the publisher, the SBC, the single board computer, will be publishing the same velocity data in that same, using that same topic. So if the microcontroller subscribe to that same topic, then it can receive all the velocity values coming from the single board computer. So it can easily move based on that. So you can take the that velocity values and you can apply that to the motors, and it can move. So it will move based on that velocity values. So that here the single board computer is controlling the microcontroller by sending velocity values. So these velocity values are sent through this method called publish and subscribe. Publish and subscribe is actually used in so many different cases, like protocol like MQTT protocol uses publish and subscribe. Other type of protocols also use publish and subscribe model. So in publish and subscribe there is a topic. There is a common topic between the publisher and the subscriber. The subscriber can subscribe to a particular topic. The publisher will send the data based on that. So there is so in this model, the advantage of this model is that there is no need to make any connection before moving. Like there is no need for any connection to make sure that there is a connection or anything like that. They don't need to be bothered about that. Like in any other kind of communication, first we need to make sure that the connections are proper, everything is connected, and you need to send acknowledgement, all those things. But here with the case of publish and subscribe model, the publisher will publish continuously whether the subscriber is subscribing or not. It will come publish continuously. So there is no need to have any connection already formed before the communication itself. Then different type of tools that are used in ROS. ROS provides an extensive set of tools for configuring, starting, introspecting, debugging, visualizing, logging, testing, stopping, distributed, com- uh, and stopping, distributed computing systems. So these are like different things that we need to. Uh, these are like different steps and different things that we need to use in any development of any kind of robotic systems. So, for example, if you take here ROS, first you need to configure the robot. Any whatever type of robot you are using, doing, like it is whether it is a slam robot or a manipulator, whatever it is, you need to configure the robot initially. Then starting the robot, initializing the robot, then introspecting means like whatever the different type of parameters it can analyze, like its current velocity, different things. And for debugging, uh, debugging, like if you have any problems, you can use different type of debugging tools to analyze the problem and rectify the problem. Then visualization. So visualization is for visualizing the movement of the robot in a real time way. Then logging means like you can log data for different type of parameter data for different purposes. Then testing and stopping. Capabilities are always provide a broad collection of libraries that implement useful robot functionality with the with a focus on mobility, manipulation, and perception. So I was provide a broad collection of this. That's one point that I said at the beginning, that beginning of a ROS explanation. First slide in ROS, that you don't need to write everything from scratch. If you need to use a SLAM, then you can use a already existing SLAM node, SLAM package in ROS. There are like different type of SLAM packages. One of them is called uh, the stack. One of the Hector SLAM is one example, and one of the examples of one of the SLAM packages with the focus on mobility, manipulation, and perception. So it can be used in case of moving, finding path, and manipulation, like direction manipulation, perception, everything. An ecosystem always supported and improved by large community with a strong focus on integration and documentation. So it is everything is well documented. Whatever package that you're using, everything is well documented. If you spend some time, you don't need anything else. You can just read the documentation and you can create your own ROS applications. So ROS key features like hardware abstraction and low-level device control, programming language independence. So it is not. Another thing about programming ROS, you can use multiple programming languages. You can use Python, C++, or Java. You can use other type of XML languages, and you don't need. But you can not just you can. You need to use multiple languages to write a single make a single ROS application. You need to write multiple languages. So all these things need to be integrated to make a single application. So it is not dependent on one single language, and it doesn't have to be written in a particular language. You can decide if you want to use C instead of C++, you can use C, or if you want to use Python everywhere, you can use Python. It depends on the type of thing, availability. Like if you have a device and that you need to connect that device, and only way to access the device is through the device driver is through you can write a device driver using C program. So that means if it is only it can be only done through C programming, then you have to use the C program. Otherwise, if it is possible to write in Python or any other language, you can use the same language. So mostly ROS is message passing between processes, OS independent. So OS independent, like I said, the heterogeneous collection of different type of hardwares. So it is OS independent, the message passing. Standardized package management is available, and useful set of shell commands and utilities with the tab completion are also available in ROS. So ROS is mostly implemented in Linux, in Ubuntu Linux OSs. So ROS distributions are very similar to Linux distributions. That is a version set of ROS packages. Each distribution maintains a stable set of package up to the end of life. So if we take Linux distributions, like there is like 16.02 LTEs, 18.02, 20.02, and 22.04. This type of new distributions are available, and old distributions are obsolete. We can use them, but they won't be useful in most cases, because if we want to use some new softwares, we have to install the new version. We need to install the new distribution of Linux. The same way, like the Linux is updated regularly. The same way, ROS is also updated year wise, or in within 2 years or something. They'll update each new distribution. So each new distribution will have something that will have everything that already implemented in the previous version, and also will have some new things implemented. So it is always better to use the newest distribution. Each distribution maintains a stable set of core packages up to end of the life of the distribution. The distributions are fully compatible with Ubuntu, and most of the ROS distributions are planned according to the respective Ubuntu versions. So it is always mostly implemented in a Ubuntu environment, whether it is a 86 architecture or ARM or whatever it is, but whatever hardware that we are using, 32-bit or 64-bit, whatever hardware we are using, is mostly implemented in Ubuntu environment. And latest ROS distribution recommended for the use from the ROS webpage. You can visit this website here, and you can find out all the different type of distributions. So these are some of the three examples here. So ROS Kinetic came, it was released in May 23rd 2016. So it's the end of the life already ended 2021. And ROS Jade, so May 2017, it's ended in 2015. It was so the ROS Indigo, April. So these are like different versions, different distributions of ROS. ROS concepts and components. So ROS client libraries are available in all these different languages: Python, C++, Lisp, MATLAB. So you can use so many multiple languages and tools, platforms, frameworks for implementing ROS. And experimental client libraries in Java and Lua. So supported operating systems: Ubuntu. It can be supported operating system Ubuntu 14 plus ROS Indigo. So this is like an old case. So we can use Ubuntu 2022 LTS to implement ROS, and we can use the latest ROS distribution in that. And Arch Linux, Debian, Fedora, Gentoo, Mac OS X, OpenSUSE, and Windows. All these OS can be used for implementing ROS, robotic operating systems. And then supported robots are like these are like already implemented robots that you can create on your own. You don't need it doesn't have to look the same. You just need to purchase the same type of hardware, and you can make this robot very easily, because these are all already implemented, different type of already implemented robots. Then different sensors that are used in ROS: 1D, 2D, and rangefinders, Sharp IR rangefinders, Acquio laser scanners, SICK lasers, Microsoft Kinect sensors, Asus Xtion. These are like different type of range finding sensors. Then then cameras, different type of cameras, like monocular and stereo cameras, different type of, these are like this is an example of a stereo camera, and USB, UVC, and rewire, video streaming, G streamer, you can use G streamer for video streaming, and different type of sensors. Then another type of 1D rangefinders, cameras, force torque touch sensors, motion capture sensors, pose estimation, IMU and GPS sensors. So GPS and IMU can be used for IMU. In IMU we can use a gyroscope, magnetometer, accelerometer, or you can use an MBU sensor. You can use a single IMU sensor with all these things inbuilt in that. So if you take an IMU, it will have a gyroscope, accelerometer, and magnetometer, everything inbuilt in the same sensor. So you can use that for pose estimation, and then GPS also can be used for localization. It won't be like accurate like other local map or localization, but for outdoor navigation we can use GPS. Audio and speech recognition, RFID, sensor, actuators, dynamic cell, fidgets, Arduino, Robotics, Lego, and NXT, and so all these sensors and actuator classes can be used here. In simulator, so you don't need to have so that is one advantage of studying ROS. You don't need to have all these hardware to create your own robot. You can do this using simulators. So there are two types of simulators: are there 2D simulators and 3D simulators. It will be better to use 3D simulators like Gazebo. So Stage is a 2D simulator for multiple mobile robots, models for sensors, laser, sonar, actuators. All these things are available in the simulator. Then model for simple objects like limited manipulation, like arm and different things are there. No physical model at all. Example, function, friction, collision, and so forth. No physical models are available. Collision, friction, all those things are not available. Open source project. It's an open source project. And then Gazebo. Gazebo is a 3D. Is a 3D simulator of multiple robots in realistic, realistic environment. A realistic simulation of a rigid body physics, dynamics. Realistic simulation of a rigid body physics and dynamics with the physics and dynamics. Realistic simulation and model for complex robots, actuators, and sensors. So all these different models are available. Complex robots, already predefined robotic models are available, like all these different type of robots that we have seen here, like Turtlebot, Pioneer. Now all these things will be available in case of Gazebo, or we can add the model in Gazebo. Support provided by part of open source robotic foundation. So the same foundation that maintains ROS also supports Gazebo for development, and chosen as a simulator for DARPA, Defense and Research Project Agency, for US Defense and Research Agency, DARPA. Robot Challenge, open source project. So it's also an open source project. So these are like some of the, this is like a contemporary what is in ROS, how we can develop an ROS project. So using these different things. Now I'll show you just show an example here. Just a video file that will be helpful to understanding. This is not the hardware part here. So this is just a this is a screen capture. So here you can see, so this is a map, this is a global map. So there are two things in ROS, a global map and a local map, a global coast map and a global and a local coast map. Local coast map is this surrounding this thing that you can see here. You can see here this orange and blue color lines are there. So these are all velocity vectors. So right now it is scattered because the robot hasn't started moving. Once it started moving, it will concentrate on around the robot. otherwise it is scattered. These are all arrows actually. If you zoom this in, you can see these are all different arrows. These are all velocity vectors. It's showing noise because the robot hasn't started working, so that noise is that's why it's all scattered everywhere. And this is a room actually. This is a room, and this is the walls of the room, and there is a round object here. This is a solid object, and there is a table here. So the robot is only allowed to go in these white spaces. Whatever white space we have here, all these black spaces are wall and obstacles and solid objects. So it can only travel in these white spaces. So then this is the local course map, this is the local course map, and this is the global course map. Then once you give the command navigation goal, you set a navigation goal. I can just set a navigation goal by pressing here, and I can show the direction. So now you can see instantly it creates a path. This green line is a path, so instantly it creates a path, and as it moves you can see the velocity vector is getting more concentrated around the robot. And you can see there is a thing that is you can see the velocity vector concentrated here. It going to different direction. You can see it shifting from left to right based on which way the robot is moving. So you can see it's moving here, this small arrow here that is moving, and then now it reaches the goal location, end location, and once it reaches the end location, robot will stop. It will align itself to that particular direction, and then it will stop. And you can see here goal reached. So it says it will show here that goal has been reached. So this is an example of a that is a visualizer tool that is used in ROS. That visualizers tool used, and using that visualizer tool you can so that there is an actual robot moving. It is not a simulation. There is an actual robot. I don't have the video for the actual robot with me right now, but there is an actual robot moving. So that is an accurate representation of the robot movement. So while the robot is moving, it is at the same time in that visualization software that robot is also moving. So our time is finished. So I hope this was helpful for you. So this is just an introduction to, we have just given an introduction to seminar on robotics. So you can, ROS is a very promising future, thing you can study. So there are like so many research is going on in that particular area right now, and you can study it on your own online because it's open source. Like a Linux system, it is open source, so you can study it on your own. So thank you guys. We have to wind up the class now.